Hello, this is Professor Stephen Nesheva, and I'm here to tell you about Le Chatelier's principle. We are going to go through a few examples that will, I hope, help you out in the homework. So the statement I have here for the principle is that when a system initially in equilibrium is perturbed, it responds in a way that diminishes the perturbation. So as we're going through these three examples, adding a reagent, changing the volume, or changing the temperature of a system in equilibrium, what you'll be wanting to look for is what was the initial equilibrium state and how did it perturb, how was it perturbed, and then how did the system respond in a way that did diminish that perturbation. So here's the first one. We're thinking about A plus B reacting to form C. Here it is initially in equilibrium with 8 A's, 2 B's, and 2 C's. And what we're going to do is add a perturbation, and the perturbation is 3 additional molecules of B. And there you have them. We're going from 2 to 5. So the perturbation is 3 extra B molecules. Now, how is the system going to respond? Well, it's supposed to respond in a way that diminishes the perturbation. So it's supposed to respond in a way that gets rid of some of the B's. Well, there are more B's here, and there's some A's available. So some of the new B will react with A to make C, as you can see there. And so now what's happened is that we've lost some of the A's, and of course also lost some of the new B's, and we are making some more C's, as you can see down here. And so the net result is more C, which is the product, less A than in the original. Here's our second example. We're going to change the volume, and now this is only really relevant for reactions with gases because the main leverage that changing the volume will have on this sort of system is by changing the pressure. So we're imagining now we have a different, stoichiometry here. We have 2 A's reacting to form B. Both of them are gas molecules. We have a total of 12 gas molecules, and there they are. So we're going to reduce the volume so that we reduce the volume. And the way to think about this is that we have perturbed the system by increasing the pressure. So to anticipate what Le Chatelier will predict will happen is that the system will have to respond in a way that diminishes that pressure increase. So how can we diminish that pressure increase? Well, we know that the stoichiometry is that 2 A's are stoichiometrically equivalent to just 1 B. So we could take 4 A's and convert them into just 2 B molecules. That's what I've done here. So instead of having 12 total gas molecules, now we have just 10 gas molecules. That clearly will diminish the perturbation, which was an increase in pressure. And the net result is fewer total gas molecules, of course, and that diminished the perturbation, as I said. The third case is raising or lowering the temperature. Now we have a different stoichiometry. Once again, it's just A reacts to form B. It's initially at equilibrium. We're just going to say, for the sake of argument in this case, that it is an endothermic reaction. And so we can kind of think of the stoichiometry as going something like this. An endothermic reaction consumes heat. So A plus heat makes B is, kind of a loose way of thinking about that reaction. So here we have an initial equilibrium configuration. I've got 8 A's and 4 B's. It's at some low temperature. And now we're going to heat it up. Okay, and what's that heat going to do? Well, the system will respond to this perturbation, which is additional heat, by finding a way to reduce or diminish that perturbation. And how can it do that? Well, it could convert some A into B, which is, after all, an endothermic reaction. So there's A getting converted into B. Now, as you can see, we have fewer A molecules and one more B molecule. The net result is some A is converted into B at the higher temperature. Now, the case that we just went over was an endothermic reaction where we raised the temperature, and the result was that the reaction shifted right, was spontaneous to the right. If you think about it, if it were an endothermic reaction and we did the opposite, we lowered the temperature, take away heat, that would make it spontaneous to the left. And then if we have an exothermic reaction, it's like what we started with, but instead of heat being on the left-hand side of the equation, it's on the right. An exothermic reaction releases heat. So if we raise the temperature on an exothermic reaction, that tends to shift the reaction to the left. On the other hand, if we lower the temperature on an exothermic reaction, now this is the fourth case here, then the reaction will tend to be spontaneous to the right.